Okay, some additional problems for Chapter 8. Here I'm going to have a grinding wheel. The grinding wheel is going to have some radius and some angular velocity. It tells me that that angular velocity is 2200 RPM, or revolutions per minute. First thing I need to do is convert revolutions per minute into radians per second. And I know that in one revolution there's going to be 2 pi radians. I also know that in 1 minute there's going to be 60 seconds. So now taking a look at my units, revolutions are going to cancel out, minutes are going to cancel out, and I'll be left with something in radians per second. So I'm going to get 230.4 with a unit of radians per second. For part B, I'm looking for the linear speed and the linear acceleration. To calculate those, I need first the radius. The radius is going to be half of the diameter, so 0.175 meters. And we know that the linear speed is going to be equal to the angular speed multiplied by the radius, so 230.4 and radians per second. I'm going to multiply that by the radius, 0.175 meters, and radians is again a unitless measure of it's unitless, so it's going to drop out, and I'm going to be left with 40.32 units of meters per second. Now the linear acceleration, that's going to be equal to the angular velocity squared multiplied by radius, so 230.4 unit of radians per second. Make sure I square that guy. It's going to give me a unit of inverse squared seconds multiplied by 0.175 meters. And I go ahead and I calculate this guy out to be 9289.7 meters per second squared. Now just a little bit more practice converting from revolutions into radians. We're looking at the angular velocity of a clock's second hand, and I know that it's going to have 1 revolution every 60 seconds, and I know that 1 revolution is 2 pi radians. So I multiply these guys together, and you can see how revolutions is going to go away, and I'm going to be left with 0.105 radians per second. So that was part A. Part B, it's asking me for the minute hand, and I know that that's going to do 1 revolution every 60 minutes. Now I'm going to say, well, I know that in 1 revolution there's going to be 2 pi radians, and in 1 minute there's going to be 60 seconds. So my angular velocity is now going to be 1.744 radians per second. Lastly, part C, the hour hand. It's going to make 1 full revolution every 1 hour. Same type of deal. 1 revolution, 2 pi radians. And I know that in 1 hour there's going to be 3600 seconds, so I'm going to be left with 1.45 times 10 to the negative 4th radians per second. Problem number 18 gives us some practice using the equations of motion for uniform acceleration. Here we're going to have a centrifuge that's going to start from rest. I'll put that in revolutions per minute. It's going to finish its acceleration at a whopping 15,000 revolutions per minute, and it tells us that the time is going to be 240 seconds. I'm going to work everything in minutes here, so I'm going to divide by 60 and come out with 4 minutes. It asks us for how many revolutions did it take, so I'll just leave everything in revolutions here. First thing I need to do is solve for the acceleration. So I'm going to say that the angular velocity is equal to the initial angular velocity plus the acceleration multiplied by time, I know that that guy goes to 0, so we can see the angular acceleration is going to be the final angular velocity divided by time. So that's going to be 15,000 revolutions per minute. I'm going to divide that by 4 minutes. And you can see why I converted that over into minutes now. We're going to have 3750 revolutions per minute squared. So that's the angular acceleration. That's a huge angular acceleration, by the way. Now we want to figure out what the how many revolutions it went through. That's going to be the initial angular speed multiplied by time plus 1/2 angular acceleration multiplied by time squared. Again, this goes to 0, and so we're left with 1/2 the angular acceleration, 3750 revolutions per minute squared. I'm going to multiply that by 4 minutes. I'm going to square that, and I'm explicitly writing the units in because I'm doing something kind of funky here. So my square minutes are going to cancel out, and I'll be left with how many revolutions this guy turns, and it's going to turn 30,000 revolutions, or 3 times 10 to the 4th revolutions. A little bit more practice using these equations of motion for constant acceleration. Here I'm going to have a fan that's going to initially have some angular velocity of 850 revolutions per minute, and rather than futz with the fancy units that I did last time, I'll just convert everything over to radians, which you should do anyway because it's easier. First I convert the revolutions to radians, and then I'm going to convert minutes to seconds, so 60 minutes or 60 seconds in 1 minute. We can see that revolutions are going to cancel out. We can see that minutes are going to cancel out, and I'm going to be left with an angular velocity initially of 88.96, and this is going to be radians per second. I know that it's going to finish its journey. It's going to be at rest, so the final velocity is going to be 0 radians per second, and it's going to cover 1250 revolutions as it does this, and I'm going to say in 1 revolution, I know that there's going to be 2 pi radians, and so it's going to cover 7850 radians. Now for part A, I'm asked for what the angular acceleration is, and if I look at my equations of motion, this one right here looks like I know everything I need to know to solve for angular acceleration. I know that this guy is going to go to be 0. If I subtract omega naught from both sides and I divide by 2 and the angle that it covers, I'm left with the angular acceleration is going to be negative omega naught squared divided by 2 and the angle, and so that's going to be negative 88.96 radians per second. Make sure I square that guy to 7850, and I plug all that in and I come out with negative 0.504, and the units here will be radians per second squared. What the negative sign means is that it's slowing down, much like if we had a car that was slowing down, the linear acceleration was negative. Same for the fan. For part B, it asks me for the time. If I look at my equations, I could say now go ahead and use this guy, but it's probably actually easier to use this guy where I know that this guy is equal to 0. So if I subtract omega naught from both sides and I divide by t, I can say that my time is going to be negative initial angular velocity divided by the angular acceleration, which now I've solved for. So negative 88.96, and that's going to be radians per second. I divide that by negative 0.504 radians per second squared. The negatives are going to cancel out, and I'm going to be left with 176.5 seconds. Now a little bit of practice calculating torques. So we're given a door, and we're told that that door has a length of 0.96 meters, and we're going to apply a force to that door, and it tells us it's going to be first perpendicular to the door and then at an angle of 60 degrees to the door, so that's going to be my force. I know that the torque is going to be equal to the lever arm multiplied by the force, but we could also write that as the length of the door multiplied by the force multiplied by the sine of the angle in between them. So for part A, I'm going to say that the torque is going to be equal to the length of the door, 0.96 meters, multiplied by the force, 42 newtons, and then it's going to be perpendicular to the door, so sine of 90 degrees, which is going to be equal to 1, and I get 40.32 with the unit of Newton multiplied by a meter. For part B, pretty much the same thing, 0.96 multiplied by the force, 42 newtons. Now it's going to be sine of 60 degrees, so I go ahead and I calculate that out. It's going to be 34.92 Newton meters. For problem number 27, I have a kind of a seesaw, and I'm asked to calculate the net torque. I have two masses of equal mass. These masses are at different distances, and I know that they're going to apply a force to my rod that's equal to the weight, which is going to be the mass times gravity, so kind of my free body diagram here. I have my pivot point here, that's where I'm going to calculate my torques about. So I'm going to say the sum of the torques is going to be equal to torque 1. Torque 1 is going to be this guy right here. You can see that's in the counterclockwise direction, so I'm going to call that positive. Torque number 2 is going to be in the clockwise direction, so I'm going to call that negative. Clockwise is generally defined to be negative. So that's going to be equal to the force multiplied by the distance, L1, sine of theta. Theta is going to be 90 degrees here, so that's just going to be 1. And this one is going to be mass times gravity times L2 by similarity. So mass times gravity, L1 minus L2. That's going to be my torque. That's going to be my net torque right there. So you can kind of see that L2 is larger than L1. At the end of the day, we're going to end up with a negative net torque, so that tells us that it's going to be a clockwise torque. Remembering that negative is clockwise, so negative. Now for a little bit of practice calculating moment of inertia, so I'm going to calculate about y-axis and then about the x-axis. I have some known masses, and it's wired together by very light, rigid pieces of wire, so what that means is they're not going to contribute at all to the moment of inertia. So first thing is the definition of the moment of inertia is going to be equal to the sum of the masses and their radiuses squared. It's going to be an I. So for the y direction, I'm going to say, well, I'm going to call this distance right here y1. It tells me that that's 0.5 meters, and I'm going to similarly call this distance right there y2. You can see that's going to be 1 meter because it's 1.5 minus 0. So I'm going to have little mass multiplied by y1 plus big mass multiplied by y1 plus little mass multiplied by y2 plus big mass multiplied by y2. And I forgot to square the masses, so I better do that right now. Now you can kind of see I can factor out the y1, so I'll simply say this is going to be 2.2 kilograms plus 3.4 kilograms multiplied by y1 squared, 0.5 squared. Do the same thing over here. I'm going to just pull y2 out and say 2.2 plus 3.4, and y2 squared is going to be 1 squared. So my moment of inertia about the y-axis is simply going to be 7 with the unit of kilograms meters per kilograms meter squared. Now for the x-axis, we're going to say the same thing. However, if you look at all these guys, this distance x1 is going to be the same. The distance from the axis is all going to be 0.25 meters, so it's going to be a little bit easier. So a moment of inertia about the x-axis is going to be equal to little mass multiplied by x1 squared plus big mass multiplied by x1 squared plus little mass multiplied by x1 squared plus big mass multiplied by x1 squared, which I can kind of simplify a little bit and say that's going to be 2 times little mass plus 2 times big mass multiplied by x1 squared. So I'm just doing a little bit of simplification there. I don't have to do that, but sometimes it's kind of nice. And then 2 times 2.2 kilograms plus 2 times 3.4 kilograms, all that multiplied by 0.25. Don't forget to square it. I can see that the moment of inertia is going to be 0.7 kilograms meters squared for the x-axis. What this says is this guy is a heck of a lot easier to rotate about the x-axis than it is the y-axis. It's actually about 10 times easier. The reason for that is because the mass is fairly far away from the y-axis, giving it a very large rotational mass, so it's much harder to rotate about the y-axis than the x. Problem number 52, we're looking at the kinetic energy of an object that is rolling. The key to this one is that the kinetic energy is not just going to be equal to 1/2 mass velocity squared as it was before. Now we have to say, well, this guy is rolling, and so it has some rotational kinetic energy that is going to be 1/2 I omega squared. Now this is going to be a sphere, so we can look up the moment of inertia for a sphere. That's going to be 2/5 mass times radius squared. And lastly, it says rolling without slipping, so that tells us we can write the angular velocity to be equal to the velocity divided by the radius of the sphere. Radius of the sphere being 0.108 meters. So I can simply go ahead and rewrite this guy's kinetic energy is 1/2 mass velocity squared plus 1/2, and I'll put my 2/5 on in here. Got my mass and my radius squared, so that's from the moment of inertia. And then here I'm going to have V over R, going to be a quantity squared here. The nice thing is you can see that these radiuses are going to cancel out because of the squared right here. And also these 2's are going to cancel out. So if what I'm left with is, plus 1/5 mass velocity squared, and then of course I have this guy, 1/2 mass velocity squared, we can go ahead and just plug our numbers in, or we can simplify this. This is going to be 7/10 mass velocity squared. So we go ahead and we plug everything into this. Mass is going to be 7.25 kilograms. The velocity is going to be 3.1 meters per second squared. And don't forget, our meters per second, don't forget to square that guy. And I'm left with 48.77 joules. Lastly, we have a problem where we have somebody that is rotating. They have an initial angular velocity of 0.9 revolutions per second, and then they lift up their arms and they're going to essentially be going slower, 0.6 revolutions per second after they raise up their arms. Well, the first question is why is that? Well, one thing that we know is this thing called angular momentum, that's going to be capital L, is going to be conserved. What that means is that the person's moment of inertia initially multiplied by their initial angular momentum must be equal to their final moment of inertia multiplied by their final angular velocity. What you're doing when you're raising your arms is you're putting more and more and more mass further away from this axis of rotation. What that means is the moment of inertia has got to go up. Correspondingly, if the final moment of inertia has gone up, the angular velocity must have gone down. So it wants to know by how much has it changed. Well, if I go ahead and I divide both sides by the final angular velocity, kind of like you see right there, I can say that my final angular velocity is going to be equal to my initial angular velocity multiplied by the initial angular speed, 0.9 revolutions per second, divided by 0.6 revolutions per second. You can see the revs per second will cancel out, and so that's going to be 1.5 multiplied by the initial moment of inertia. So the moment of inertia has gone up by a factor of 1.5.